Alright guys, are you ready for the last chemistry review of the semester? Let's get it. Okay, so first things first, you're going to go ahead and log on to Pear Deck. I put the link in the chat. I want you to try to answer the questions first before looking at the answer. Make sure you record the answer and how to solve for it. There is a special task embedded in the end of the PowerPoint, so you must watch the entire video, and that's how you will receive your grade. It's easy, I promise. But I do want you to go through each problems, or at least, go through the Pear Deck, because I do give the solutions at the end. But more than likely, just watch the video, if anything. It is going to be a long video, so let me warn you. So let's just go ahead and get started. So today, we are actually going to be covering Unit 3 all the way to Unit 5, which yesterday we did cover Unit 2. I think I skipped like 1 or 2 questions, but I'll go back to them. Alright, so Unit 3, we're going to talk about the periodic table and periodicity. Alright, so on Unit 3, we're going to talk about periodic trends, the successive ionization energies, and physical and chemical changes. You can go ahead and pause and read this. I'm going to go ahead and continue just for time's sake. So, definition. The word is effective nuclear charge. What is that? It's the charge of the net. It's the charge of the net charge of an electron. Oh my god, I don't know. It's the net charge that an electron experiences in atoms with multiple electrons. It increases as we go to the right of the periodic table, which makes atoms smaller on the right side. So effective nuclear charge, the greater effective nuclear charge you have, the smaller your atom will get. Mainly why, or the reason why, it's because of that proton pulling power. PPP, right? Proton pulling power, PPP. So it increases as you go to the right, right? So this first column will have a effective nuclear charge of 1. So I have a 2. This is 3, 4, 5, 6, 7, 8. And then of course it's 2. But remember, there are positive because it's proton pulling power. So the more those protons are pulling on those valence electrons, the closer it is bringing them together. Next one is electron shielding. It says of shells in an atom, more energy levels equals more electron shielding. It increases as you go down the periodic table. So how does this trend increase? As you go down the periodic table. Electron shielding is basically the valence electrons being shielded by the inner electrons. So if you have an atom, right, this is our first energy level, you have these 2 electrons. The one has 2 electrons, which are the ones in the first row, have 0 shielding. Why? Because they're filling the entire pole of the nucleus. But if you were to be on the second energy level means the second row, right, 1, 2. So these electrons on the second row are shielded by the electrons on this first energy level, right? This is the first energy level. This is the second one, because it's the second, oops, there's something that goes there. This is the second, what do you call it? Ring? Oh, it's over there. And then basically, the more and more and more and more and more energy levels that you have, the more shielding it has. So for instance, if you were to add another energy level, now let's say this electron here, which is on the third energy level, meaning it's here, let's say it's sodium, this one, this valence electron, which is the outermost electron, is being shielded by the ones on the inner, the first energy level and the second energy level. So it has more shielding compared to the second one, because now there's more electrons blocking the pull of the nucleus. And if you were to add another row or another energy level or go on to another row, they'd have even more shielding. And the farther and farther and farther you are, the more shielding you are. The more shielding you have. Let's look at the next one. Oh, there you go. Atomic radius is the size of an atom. It increases as you move down the periodic table. So because as you move down, right, because the more shielding you have, those more energy levels, right? The more energy levels you have, the bigger the atom gets, right? So it increases as you go down, and it increases as you go to the left of the periodic table. Why? Because the effective nuclear charge is less compared to over here. These have a proton pulling power of 8, which means it's a lot stronger, so it's pulling in those electrons a lot closer, where the ones over here have an effective nuclear charge of 1, which is not pulling on that close. So if you're pulling like very weak, it's not going to go closer to you, but the more stronger you're pulling, the closer it's going to get. If it's over here, and I only have an effective nuclear charge of 1, I'm going to just pull it that much. So the atom only gets a little bit smaller. But if you have an 8 or stronger, it brings it a lot closer, so it gets smaller. Okay, let's look at the next one. Electronegativity. Oh, and let me remind you, for atomic radius, francium, which is Fr, has the biggest radius. Yes, never showed up. There you go. Electronegativity is the ability to pull electrons toward the atom in a bond, which is how much an atom can attract extra electrons or attract electrons, or like how greedy they are to get extra electrons. Well, for instance, electronegativity increases as we go over here. This is where it increases. Whoa, what happened here? It increases as we go to the right, because of the fact that, you know, there's more proton pulling power, so those protons are pulling more on those electrons, and then it increases as you have less shielding. Why? Because the pull of the nucleus with less shielding, let's say we're comparing this one to, I don't know, this one, and we have a valence electron in here, valence electron on here. The electron is the nucleus is closer to this one, so it's holding on to those electrons and it's pulling it a lot more compared to here. It's super far away, so it's not going to be able to pull in extra electrons, where this one, it's super close, it's going to be able to pull extra electrons.
You have about 25 minutes left.
That's why it's a lot harder. And then that one is fluorine. Fluorine has the greatest electronegativity. On your noble gases, they have 0 electronegativity. Why do noble gases have 0? Well, because they already have their full 8 valence electrons. They don't want any more. They already have their 8. They already have their 8. Oh my god, why is this thing not writing? Well, they have their 8 valence electrons. They don't want to add any more extra electrons because they already have their full 8. They don't need any more, because if not, then they have to make a whole new energy level. And remember, they want to have their whole octet rule full. Ionization energy. Ionization energy is the amount of energy required to remove an electron, which I want you to think of the E in energy to be on this side. Remember how we do the near, N-E-A-R? E is over here, which is ionization energy. So it increases as we go to the right and as we go up. Same thing with electronegativity, right? E, electronegativity, belongs in that corner, except the one that has the greatest is helium, right? Main reason, if you were to actually draw helium out, the electrons, it has 2 electrons, and it's on the first row, right? It's on the first energy level, only has 2 electrons. So the nucleus is pulling very strongly on those 2 electrons. These electrons also have 0 shielding, so there's nothing blocking it from the pull. Remember, electrons are negative, protons that are in the nucleus are positive. They're attracted to each other, so it's pulling on those electrons very strongly, and it's not going to want to give them up. So that's why it has the highest ionization energy. Basically, all of your noble gases have the highest ionization energy. Main reason why, well, all these have a proton pulling power of 8, your Zeph of 8, and the fact that it has 8 valence electrons, it's complete, it's happy. It doesn't want to give up their electrons, so it's going to hold on to them very tightly. And then ionic radius. This trend is a little bit harder. I do want you to know that negative ions, so negative ions are larger since they have less protons. Oops. Twice, are larger since they have less protons than electrons, and then your positive ions are smaller, which makes the effective nuclear charge less when you have negative ions. So negative ions are always larger since they have less protons than electrons, making the effective nuclear charge less. So that's the reason why. Alright, one thing that I also did want you guys to remember is the near. I wrote it in the near in black. So N-E, I think it's opposite, E-A-R. I think that's how my video goes. So N-E-A-R, which N stands for nothing. Nothing increases in that general direction. For ionization energy, you have two things, which is ionization energy and electronegativity. Also, effective nuclear charge technically increases, but only to the right. It's the same on the on the columns. Here at the bottom, down and to the right is the atomic mass and atomic number. And here to the right, or to the left, it's radius and reactivity. It increases as you go down and to the left. The chart below shows the relationship between ionization energy and increase in atomic number. The letter on the chart for the noble gas group 18 is most likely, so we're looking to see which one are your noble gases. So first things first, let's go ahead and see what our chart is made up of. There you go. So here on your y-axis, you have the ionization energy increases. So this one is probably the one that has the greatest ionization energy. Here you have the atomic number increases. So if you notice, as the atomic number increases, the ionization energy actually gets lower. So when you have a low atomic number, right, you should have a high ionization energy. But let's figure out which one has the greatest ionization energy. So out of all of these elements on the periodic table, that is helium. Helium has the greatest ionization energy. So this one is most likely helium, which means these other ones are probably neon and argon. So that means that our group 18, which are your noble gases, so all of these here are your noble gases. Let me type it that way. Noble, oh, there you go. Those are the ones that have the greatest ionization energy. So your answer is X. All right, go ahead and pause the video so you can work on this problem. So it says valence electrons in an atom of phosphorus are closer to the nucleus than valence electrons of aluminum because, so we're comparing two. We're comparing phosphorus, which is right here, and we're comparing aluminum right here. So we're comparing these two. Which one has the greater effective nuclear charge and which one has the greater shielding? Well, for effective nuclear charge, remember, it's the same thing as finding the valence electrons, except remember with Zeph it has positives in front. So phosphorus has a Zeph, right? This is your Zeph, an effective nuclear charge of 5. Aluminum has 3. So which one has greater? Phosphorus has a greater effective nuclear charge. So we can go ahead and cancel out C and D because phosphorus has the greater one. Now let's talk about the shielding. Which one has the greater? Do they have greater shielding or the same shielding? Well, shielding is based off of the row. I see that both of them are on row 3 of the periodic table, so they have the same amount of shielding. So your correct answer is B. So it's closer to the right.
Exactly 15 minutes left.
Same electron shielding and the effective nuclear charge increases. Let's look at this next problem and go ahead and pause, watch the video, pause. Oops, I might have saw the answer. So it says, which term refers to how strongly an atom of an element attracts electrons in a chemical bond with another atom? So this one you need to know the definition. Remember, this one's talking about the attraction of electrons. Look at the wording. Remember, ionization energy is how much energy is required to remove an electron. So that's not it. I'm not talking about removing electrons. We're talking about attracting electrons. Atomic radius is the size of the atom. Nope. Melting point, the ability to melt. Nope. I like at what degree. And electronegativity? Yes, electronegativity is your answer because you need to know the definition, which is how strongly it wants to attract electrons. Which statement describes the general trend in the electronegativity and first ionization energy as the elements in period 3 are considered in order from Na to Cl? Go ahead and pause the video. So here I have sodium and chlorine. I have sodium right here, Na, And then I have chlorine over here, Cl. So as we're going from sodium to chlorine, does electronegativity increase, decrease? Or do they both, or does ionization energy decrease? Or do they both increase or decrease? Well, this is one where you need to know the trends. Remember the one that I told you to remember? Near. So you here, an E here. It's going to pop up somewhere. My N and E, hopefully. Oh, there you go. N, E, and then down at the bottom is A, and then down over here is an R. But I only put like half the periodic table. So E, remember, E stands for electronegativity and ionization energy. So it does stand for both of those letters. So ionization energy increases as we go to the right, and then it goes up. So both of these are on the same row, but you can see that from sodium to chlorine, they both should increase. So electronegativity and ionization energy both increase because they're both trends increase to the right. Which of the following has the smallest ionic radius? Go ahead and pause the video. Remember, to find the ionic radius, we know that for ionic compounds, the negative, if it has a negative charge, that means it will be bigger. The more positive it is, the smaller it is. So because +3 is like, plus the +3 is the most positive out of all of those, it would have the smallest ionic radius. If it was asking for the biggest ionic radius, it would be P with the 3 negative charge. Because the more negative it is, the greater it is. Due to the fact of the Zeph that it has, and it lost electrons. All right, let's go ahead and talk about successive ionization energies. Successive ionization energy is the amount of energy needed to remove an electron from two, then 3 electrons. It increases as you go up, since there are less shells and increases, and the electrons are more attracted to the nucleus, so more energy is needed to remove them. And then decreases as you go to the right, since they are closer to being full and really want the electrons, so it will take more energy. So nitrogen has a greater ionization energy than phosphorus. What is the best evidence to support this observation? Go ahead and pause the video so you can answer the question. All right, so we're looking for nitrogen. Nitrogen is right here. Phosphorus is right here. So which one best supports how nitrogen has a greater first ionization energy than phosphorus? Which direction does it increase? So nitrogen has a greater effective nuclear charge. No, that one's not it, because why? They both have the same effective nuclear charge. Remember, 1, 2, 3, 4. They both have an effective nuclear charge of 5. They're both the same, so that's not it. Nitrogen atom is larger than the phosphorus atom. Remember, radius increases as we go down and to the left. This is where our radius increases. So nitrogen is actually smaller because it has 1 whole less energy level. The electron ionized from nitrogen is in a lower energy level, closer to the nucleus. So technically it is. This one's in the 2nd energy level.
10 minutes.
Phosphorus is in the 3rd energy level. The electron ionized from nitrogen is from a core energy level. No, it's not from a core energy level. The correct answer is C. All right, let's go ahead and talk about physical and chemical changes. Remember that chemicals are not easily reversed, new products are formed. Just basically remember city girls like to party, which is C, is color change, girls, gas, produced, light is produced, T is temperature change, P is a precipitate is formed. Also there's like bubbling, smell, those ones. Physical, they're easily reversible, no new products, often just state a change. For instance, if ice is melting, that is a phase change, and then if it's turning into a gas, that's also another phase change. But it's all still water. So which of the following does not count as evidence of a chemical change when a candle is burning? Go ahead and pause this one. You can answer it. Oops, sorry. So which of the following does not count? We're looking for the one that does not count as a chemical change. So light is given off in the process. So we know that light is one of the city girls like to party. Light is a chemical change. Soot forms on the bottom of the surface held near the top of the flame. So this is like the burning part of it. So soot is a new, and it says it's soot forms, so that's something new that was produced from it, which is like the burning parts of it, which we know when things are burnt, it is a chemical change. Wax melts and vaporizes at the wick. So that means it's talking about this part, the waxing of the candle. I mean, when it melts and then it dries up or like gets hard again, isn't it still wax, right? It's still the same thing, so this one might not be it. The flame gives off heat as the candle burns. It has heat, so it's a temperature change, and it even says burns. So yes, definitely it's not this one because that's a temperature change, so your answer is C. All right, let's go ahead and move on to Unit 4, bonding. Okay, so for Unit 4, bonding, we're going to talk about ionic versus covalent compounds, drawing Lewis diagrams, VSEPR theory, polarity. So you can go ahead and pause the video so you can read what you are expected to do. And let's go ahead and look at ionic bonding. So ionic bonds are made up of metals and nonmetals. They conduct electricity and are much stronger than covalent bonds. So here I made a periodic table. It looks really bad. Don't judge me. But you know how you have that staircase on the periodic table, right? It's like right here. Well, all the ones on the left side, all these are metals, and these are nonmetals. So whenever you have one from this side and then one from this side, you have an ionic compound. Main reason why it's because the nonmetals really want extra electrons because they're highly electronegative, and the metals, they really don't need their electron, that valence electron, so they'll end up giving it away or sharing. They'll give it away, not share. They'll steal it. Where covalent bonds are made up of two nonmetals, they're very weak compared to ionic bonds, and they do not conduct electricity. So if we were to have our periodic table, it looks something, a little something like this, right here. Remember, there's still that staircase. These are your nonmetals on this side. And well, that's when you have two that are on the same side. That's when you have a covalent compound because they share electrons. All right, so this is a cute little cartoon to help you understand why. Here in ionic compounds, they are, the anion is giving the cation, which is the blue one here, it's giving up its electron to the anion. That way it can have its full 8, it can be complete, it can be happy. Where here, with covalent compounds, they follow the octet rule. They're buddies. They are sharing electrons so they can be happy and complete the octet rule. Sorry. Okay, I'm done. Next one. It says, what combination of two elements would most likely form an ionic solid? So this one, you do need your periodic table. You need your periodic table, that way you can see more or less where they fall. V has 1 valence electron, W has 2, X has 5, Y has 6, Z has 1, 2, 3, 4, 5, 6, 7 valence electrons. You don't know where they are on the periodic table. Well, if you look at V and W, V has 1 valence electron, which means it would, when it gives up its electron, it would have a charge of +1. W has 2 valence electrons, so when it gives up its 2 electrons, it would have a +2 charge. X has 5 valence electrons, so when it gives up some of those, it would have a -3 charge. This one, Y, has 1, 2, 3, 4, 5, 6 valence electrons, and Z has 7 valence electrons. If we're looking at the periodic table, I should have posted it on here, but I didn't, and I'm so sorry that I didn't do that. If we're looking at the periodic table, V would be in this column because it has one valence electron. So this column right here, this is V's column. This one right here, this one has 2. This would be W. And then we have X, Y, and Z. They're here. Sorry, this looks really bad. This would be X, this is Y, and this is Z here. Main reason why, because it has 5, 6, 7 valence electrons. These have 1 and 2. So 3 and 4 would go here, 8 would go over here. So now we can definitely see the difference between where we have our ionic and where we have our covalent compounds. So whenever we have a metal and nonmetal, let's see, look over here, metal and nonmetal, that would be ionic, because metals, they tend to form positive charges, nonmetals tend to form negative charges. So V and W, if we were to have V and W, would have positive 2. So no, we actually need a negative 1. X and Z, X has a negative 3, Z has a negative 1, or 5 and 7 valence electrons. Nope, they're both nonmetal, so that's not it. V and Y, V has a positive charge, or 1 valence electron. Y has a negative charge, which is 6 valence electrons. So yes, those can form an ionic compound because it's a metal and a nonmetal. And X and Y, they're still both negative, so they would not form an ionic compound. Oh, oops. So let's look at the next one. Based on the Lewis dot structure for these elements, which of the following is the correct formula for a bond between X and V? So if we look at X and we look at V, remember this one, these two were your metals. These over here are your nonmetals. So we're going to have V and X, right? V has 1 valence electron. X has 1, 2, 3, 4, 5. Right? 5. 1, 2, 3, 4, 5. We know that the metal tends to give these electrons to the nonmetal. So this electron would come over here. It would come over here. So I notice that these two are still single, so that how many more V's do we need? I think I'm going to have to add another one. So it can come over here. And I think I'm going to have to add one more. That way that electron can come over here. So that the X can have a total of 8. So what is our formula? How many V's do we have? Remember, we always write the metal first. 1, 2, 3 V's. And then how many X? Just 1. Our answer is C. This is also another way you can do it by getting the charges and do the crisscross method. These have a charge of +1. X has a -3. Crisscross, so you need a total of 3 V's and 1 X. All right, let's look at this next question. It says a solution in the beaker A conducts electricity, where the solution in beaker B does not conduct electricity. Right, you can kind of tell by the little light. Based on the data, which answer choice lists possible options for solutes in each beaker? So I know whenever they conduct electricity, it needs to be ionic. I don't know where my little cursor is. I think it's over here. Wow, I couldn't see. Ionic, and this one should be covalent because it does not conduct electricity. Or you can think of this as an electrolyte and non-electrolyte. Remember, electrolytes are ionic compounds, which means they need to have a metal in there. So you need to look at your periodic table. Na, is Na a metal? Yes, it's a metal. N and O and N and O, these two, is probably going to be polyatomic. Those are non-metals. So metal, non-metal, that's ionic. Carbon, non-metal. I'm going to put Nm for short. Hydrogen, non-metal. O, non-metal. H is non-metal. So this is made up of a bunch of non-metals. So this A looks like it could be our answer. Sodium's a metal. Cl's a non-metal. So that's ionic. B, Ag is a metal. N and O together are both non-metals. So this is also ionic. So here we have both of them ionic. B is not our answer. We have metal, non-metal for both. Beaker A, you have a non-metal. Well, we said C2H0. These are a bunch of non-metals, so no. Na is a metal. Cl is a non-metal. So metal, non-metal, that's ionic, which remember for B we want it to be covalent, so C is out. Last one, Pb is lead, that's a metal. And an O, those are non-metals. So metal, non-metal, that's ionic, which is what we want for beaker A. K is a metal, and O is non-metal. This is also ionic, but for beaker B, we wanted it to be covalent. So your answer is A. There you go. So only metals conduct electricity. That's ionic. Covalent compounds, it's non-metals only. All right, let's look at the next problem. You can go ahead and pause so you can answer it. Okay, so A and B represents unknown elements. Based on the Lewis dot structures for these elements, which of the following is the correct formula for ionic bond formed by these elements? So here we have A and we have B. And we're looking for the ionic, I can't see my little cursor, ionic bond formed by these elements. So we don't know what these elements are, but we're looking for the formula. So if I were to have A, right, and it has 2 valence electrons, and B, which has 1, 2, 3, 4, 5, I'll put the electron over here, 6, 7, and this is ionic, so that means one of them is going to steal the electron, so this A is going to give 1 electron over here. This is where the electron is going to go. Okay, but now A still has 1 more. We can't put any more on B due to the fact that it already has its full 8. So which one do I need more? Do I need another A? No, right? Because I mean, if I add another A, I'm going to have 2 more electrons. But if I add 1 more B, which has 7, can't this one go over here to the B? Yeah, that way that electron goes over here, and now B has its full 8. So what is our formula? When we write our formula, we're writing how many of each atom we have. So here I have 1A, right? And I have a total of 2B. So our answer should be AB2. This is just another way of doing it, where you put the charges of them. Remember, if they have 7 valence electrons, they have a charge of -1. If they have 2, they have a charge of +2, and you do the crisscross method. All right, now we are going to draw Lewis diagrams. Remember what the octet rule is when they have or share 8 valence electrons. When they want 8 valence electrons. When they share, remember a bond is worth 2 electrons. It says the correct Lewis structure for BF3 would have exactly, oops. So if we look at BF3, you draw boron, right? That's the middle one. You draw 3 fluorines. Oops, I'm doing it so wrong. 3 fluorines. Oh my gosh. I'm doing it so wrong. Well, I'm not doing it wrong, but I was supposed to go in order. So boron has 3 valence electrons. So 1, 2, 3. Fluorine has 7. 1, 2, 3, 4, 5, 6. This one that's bonding makes it 7. Fluorine has 7. 1, 2, 3, 4, 5, 6. This one makes 7. 1, 2, 3, 4, 5, 6. This one makes 7. Oh my gosh, I'm so sorry. So this is what BF3 looks like. Notice that it has 3 single bonds, 0 double bonds. So your answer is C. How did I get those dots? Well, if you look at boron on your periodic table, boron has 3 valence electrons. And remember, we count the valence electrons by the columns that they're on. So this is 1, 2, boron's on the 3rd one, 4, 5, 6, fluorine is on the 7th. That's how we know it has 7 dots. Sorry about that. I just went ahead of myself. All right, which of the following Lewis dot diagram is incorrect? So we need to draw them out. So here I have drawn all 4 of them out. This is the correct drawing, so which one is incorrect? It's going to be C. So what I definitely recommend to you all to do is to draw it out yourself. So for instance, I'm going to show you the example of C bonded with C, carbon. Carbon has 4 valence electrons, right? And then another carbon also has 4. Remember, we bond all the single ones. So this one's going to bond, this one's going to bond, this one's going to bond, and then these over here are going to bond. So how many bonds did I create? I have 4 bonded together, like that. So that's how we get our C bonded with C. So this is the one that does not look correct. All right, let's look at the next problem. It says, which of the following particles has a central atom that does not obey the octet rule in its most stable form? So remember, the octet rule is where you have to have, or they're sharing 8 valence electrons. So we can go ahead and draw each one out. Oops, I went too ahead. I'm going to go ahead and draw HCN. I'm going to draw kind of fast. Yeah, which looks like this. That's HCN. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. So here's 1, 2, and then it's sharing with the 5. And we're mainly focusing on the central atom, which is carbon. H2O is water. Water looks like this. And I'm sorry I'm not showing you guys how to draw them. You should already know for one. Oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, 6. That's why they doubled up. Hydrogen has 1, so they bond. BeH2, so beryllium has 2 valence electrons, right? 1, 2. Hydrogen has 1 each. This one I'm actually showing you. And then you bond the single ones. Boop. Boop. There you go. PCl3, phosphorus has 5 valence electrons, 1, 2, 3, 4, 5. There's a total of 3 chlorines. Each chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Remember, I want you guys to go in order like this. 1, 2, 3, 4, 5, 6, 7, but for time-wise, I did it the fast way. Anyways, we bond all the single ones. So this one single likes to mingle. This one will mingle with that one, and this one will mingle with that one. There you go, perfect. Now, which one breaks the octet rule? So we need to count how many electrons are in the central atom, or they're sharing. So remember, each bond is worth 2. We're going to focus just on carbon. So right here, how many electrons is sharing? 2, 4, 6, 8. This one has 8. Let's look at oxygen. Oxygen's our central atom. 2, 4. These two make 6. These two make 8. Let's look at beryllium. And I'm only doing the bonds that beryllium is sharing. So beryllium has 2, 4. So this one does not have 8. Like this one has 8. And let's look at PCl5. And PCl3, not 5. Just kidding. Oh my gosh. Alright, so each bond is worth 2. So 2, 4, 6. These two make 8. So this one also has 8. So the only one that did not have 8 is BeH2. Alright, and now next is the VSEPR theory. Go ahead and click this link so you can open up your VSEPR chart. So it says, what is the molecular geometry of carbon dioxide? If you look at your VSEPR chart, it's going to look a little something like this. You guys do have access to that. You will have it on your review. It's going to be at the very, very end. So what is the molecular geometry of carbon dioxide? CO2. You got to draw carbon dioxide out, which looks like that, right? Carbon has 4 valence electrons. Each oxygen has 6. You bond the 2. And it looks like that. Notice that carbon has 2 bonded atoms, which when you look at your VSEPR chart, you are comparing. Let me see if I can show you. No. That's okay. When you're looking at your VSEPR chart, you have the total groups of electrons, which is the number of your steric number, which is the number of attached atoms and lone pairs on the central atom. Then you have your bond angle here, where it says number of bonding directions. Number of bonding directions. That is how many atoms do you have attached. So here in this example, we have 2 atoms attached, right? And there are 0 lone pairs left on the central atom of oxygen. So that means we have a linear shape. That's where we get it from. Let's look at the next one. What is the molecular geometry of IF3? So that means you have to draw it out. Iodine goes in the center. Iodine has 7 valence electrons. I actually want to draw this one out with you. So iodine's in the center, has 7 valence electrons. And then we have to draw a total of 3 fluorines. 1, 2, 3. Each fluorine has 7 valence electrons also. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Alright, so for sure we gotta bond all the single ones, because the single ones they like to mingle. Where's my little colors? Here it is. So these two for sure you can see are single, so I'm going to bond them, right? That's like the first one you should bond. But now I don't see any more leftover single ones on iodine. I can't bond the fluorine to fluorine, so that means I'm making a new molecule. I need to bond them to the iodine. Oh, I accidentally clicked my watch. Sorry. So, I don't know where my cursor is either. This one, we're going to break up that lone pair on top. So that one can go there. And this one can go right there. See how we broke up that lone pair? Now, when we draw it out, we have the fluorines. But now we have 2 lone pairs because of these 2 here. That's 1 lone pair, that's a second lone pair. So this is what it looks more or less like. So, how many attached atoms do we have on here? We have a total of 3 attached atoms. Right? Or you can also look as the regions of repulsion or your steric number. I think that's probably the easiest part. Where's my little colors? We're going to use green to identify our regions of repulsion. So each atom attaches 1 region. So 1, 2, 3, plus the lone pairs 4, 5. We have a steric number of 5. So I can look for steric number 5, which tells me for sure it's going to be between these 3. Or you can look at how many atoms do you have attached. Well, I have 3 atoms. You can look at all the ones that have 3, 3, 3, 3. Then you can also see, okay, how many lone pairs do I have? I have a total of 2 lone pairs. So 3 atoms attached, 2 lone pairs, gives me T-shaped. So here we have it. This is what you should have drawn. So it has 3 bonded atoms. I'm probably going to shorten it, put BA, and 2 lone pairs, LP. All right, which of the following would have a trigonal pyramidal, oh my god, I can't say it, geometry. Trigonal pyramidal geometry, there you go. So you need to draw them out. Remember, whenever they have that negative charge, like this one has a -1, that means you're going to add an electron. Let's draw them out. I'm going to draw them out very carefully for you all. NO2, so that means you have 1 nitrogen, 2 oxygens. Remember, nitrogen has 5 valence electrons. Each oxygen has 6. 1, 2, 3, 4, 5, 6. And then we're going to bond the single one. So this one's going to come over here. For sure, this one gets bonded. And then I have this one here, which is going to bond to that one. But now I still have this bottom single one, right? You see it here at the bottom? I can't break up that lone pair because that means that lone pair is going to have it. But because of this -1, that means we're going to add an extra electron. I'm going to go ahead and change the color of that electron that I'm going to add. We'll put dark green right here. That's my extra electron that I added. And now it has the lone pair. We can go ahead and figure out what geometry shape it has. Remember, there's a total of 2 atoms attached, right? So there's 2 oxygens, and there's this 1 lone pair on the top. So, bonded atoms, we have 2. Lone pair, we have 1. So that means our steric number is 3. Right? If you add up the 2 and the 3, 2 and the 1, it gives you 3. It has 2 lone pairs. I can't really see. 2 lone pairs, 1 two bonded atoms, one lone pair, and that gives us a bent shape. So that one's actually bent. So it is not this one. So A is out. You're going to do the same thing for the rest of them. O3, I'm actually just going to show you the answers. Oxygen has 6 valence electrons. Each one has 6. You bond it, creates 2 double bonds, and it's in the bent shape because of the fact that it has this lone pair right here on top. That one lone pair, 2 atoms attached. And then, just like this one was the bent shape. This one's also bent. Oh, I already put it there. This one, it has 2 atoms attached and 2 lone pairs. And when you look at it, it has a steric number of 4, because 2 plus 2 is 4. 4. And then you look for 2 lone pairs, 2 atoms attached. It is also in the bent shape. So that means it's probably going to be D. And if you look at D here, it has 3 bonded atoms, right? Because there's 3 chlorines and only 1 lone pair, right? This lone pair here. So that means their steric number is 4, because there's 4 regions of repulsion. So 4. And then if we move on here, it has 3 atoms attached, right? Because there's 3 chlorines. That 1 lone pair, which means it's a trigonal pyramidal. So the answer is D. If you guys don't know how to do it, do the axe for them. If you draw them out, you can do the axe. The answer has the axe given to you there too as well. All right, the geometry of SO3 molecule is best described as, we can go ahead and draw that one. Sulfur is our central atom. Sulfur has 6 valence electrons. This is what it looks like. I went in order, 1, 2, 3, 4, 5, 6. And then we have 3 oxygens, 1, 2, 3. Each oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I hope my dots come out. So for sure, you gotta bond all the single ones, because singles like to mingle. So I'm gonna bond this one with this one over here. Can't see my bonds. This one will bond with this one. Why can't I see my bonds? Okay, let's do this again. There you go. That one bonds with that one. This one will bond with this one. Oh, the electrons didn't show up. There you go. And then we have to break up this lone pair, right? We have to break it up so that way it can bond with the oxygen. And that one will bond with that one. Now, I have this lone pair and I still have 2 single ones. So I'm going to break up that lone pair. One of them's going to come over here. And one of them's going to come right here. Right? It looks super messy. But when you redraw it, you'll see that it actually creates double bonds with each one. So I don't have any lone pairs, right? There's 0 lone pairs and there's 3 atoms attached. So we're going to look for 3 and 0. 3 and 0 gives me a trigonal planar. Right? This is 3, 0. So your correct answer is A. Next one, which of the following molecule is not adequately described by the following geometry? So you do need to draw them out again. And then, well, I'll help you draw them out. It's okay. Because it takes a while to draw them all out. So I'll draw them kind of fast. Xenon has 6 valence electrons. It has 8 valence electrons because it's a noble gas. So 1, 2, 3, 4, 5, 6, 7, 8. Each fluorine has 7, which means it has 1 single one ready to bond. So we can actually share these here, which means it will have 2 lone pairs. So we can look at our periodic table, our VSEPR chart has 4 bonded atoms, 2 lone pairs, so we're going to look for 4 and 2. I'm gonna look for 4 and 2, or you can add them up. Look at 6. 4 and 2 is 6. So 4, 2, we have a square planar. So that's not it. We can do the next one, SO4. My thing's being super laggy. It's probably because it has so many slides. SO4. So sulfur has 6 valence electrons. Oxygen has 4. 1, 2, 3, 4. I mean, there's 4 oxygen, each with 6 valence electrons as well. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I heard that one. There you go. The bond the single one, so this one's gonna bond with this one. This one's gonna bond with that one. I have to sneeze. Well, for sure, all of them go bonded once. So this one's gonna bond here. This one's gonna bond here. And then this one has to bond here. This one's gonna have to bond here. All right, now there's no more bonding with sulfur. But because of the fact that it has this -2 charge, we get to add 2 electrons. So I'm gonna add one here and add one here. That way these can be a pair, these can be a pair right here. Okay, now it's working. We said this is a tetrahedral because it has 4 side atoms, or 4 atoms attached, 0 lone pairs, and this one was a square planar because it has 2 lone pairs, 4 atoms attached. Now let's go ahead and draw the next one, which is XeO4. Xenon again has 8 valence electrons. Oxygen has 6. And with oxygen, they're going to bond 2 of those single ones in the oxygen to 2 lone pairs. So it's going to be like that for every oxygen. It's going to have double bonds. Which this is also going to be a tetrahedral. So notice that both of these so far are tetrahedrals. And then PO4 with a -3. It's not showing up, so I'm just going to go ahead and skip the next slide. Looks like that. If you notice here, PO4 is also a tetrahedral because it added 3 electrons. This is where they added 1, 2, and then, hold on, not there. Already there. I forgot a lone pair. And then this is the third one. So those are the 3 electrons that were added that way, because usually they have 6, so it would look like it would have a double bond, look like that. But because of the fact that they added 1, in each one it has single bonds. So all of these 3 are tetrahedrals except for this one, which was a square planar, because of the fact that it had 2 lone pairs on the central atom. All right, now last problem for topic number for unit 4 is polarity. What is polarity? Remember, it's the difference in electronegativity that leads to electrons spending more time on a certain section of the molecule. It's asymmetrical and are usually polar molecules. So one thing I do want you guys to remember is we draw dipoles. Remember, it shows the positive N. It's just basically an arrow showing the pole of electrons. And then on the opposite side would be the positive tail, where the more than likely the element's going to be positive. So for instance, let's look at H bonded with F, fluorine. Fluorine has 7 valence electrons, right? Fluorine is also the most electronegative element on the periodic table. So if I'm going to draw the bond, or the electrons, there's going to be more electrons around the fluorine than there is around the hydrogen. So that's why you see it's bigger on this side. So we draw our dipole facing toward the fluorine, giving hydrogen a positive tail. So what's happening is with those electrons, right, the electron is actually a lot closer to fluorine than it is the hydrogen. So like pretend like this is the bond. The bond is a lot closer to the fluorine. That electron is being pulled towards fluorine, and instead of being close to the hydrogen, so leaving it with a positive charge, even though it's still technically hydrogen's electron, it's just closer to fluorine. So it says, consider what you know about the polarity of water. Which of the following molecules is not soluble in water? So one thing that we need to know about water, water is a polar molecule. So water is H2O, which is polar. So we need to figure out which one of those is not polar, right? Because water is H2O. Once you have an oxygen, bond it with two hydrogens, looks like this. And remember, polarity goes, if you look at the periodic table, the one element that is the most polar is fluorine. So any element close to fluorine is highly electronegative, which means more than likely, if it's somewhere far from fluorine, it's going to be polar. So for instance, oxygen is there, really close to fluorine. Hydrogen is far away, so they create polar bonds. So water is a polar molecule. And in order for you to be soluble, remember, it's like, dissolves like. So that means the same would dissolve the same. So another polar molecule can dissolve or is soluble in another polar molecule. So we need to look for the one that would not be soluble, so which is the one that is nonpolar. So your answer is A. And the reason or way that you get A is if you look at all the other polar ones. If you see that there's a lone pair on the central atom, it is polar. These here show the dipoles. Whenever you have dipoles that do not cancel out, so that means this half of the molecule that is on the top is polar, where the bottom half is nonpolar, but that means the entire molecule is polar. Same thing here. The overall net dipole would be going up because there's no other dipole that's canceling out that one that's facing up. Where here, you have one facing up, one facing this way, one facing this way, one facing that way. They're all canceling each other out because they're all pulling in different directions. So your answer for this one is A. Now let's go ahead into Unit 5, which is solutions. So Unit 5, we're going to be covering molar conversions, concentration models, molarity calculations, making solutions, and solubility curves. So you can go ahead and pause to read what you are expected to do. So first thing, what is a mole? Remember, the mole is a quantity just like a dozen, except that number is 602 sextillion, which is a super, super huge number. It's not the animal, the mole, but it's the number. 6.02 times 10 to the 23rd, which is Avogadro's number. And we know that 1 mole is equal to Avogadro's number. Molar mass is basically the mass of 1 mole, where you put 602 sextillion particles on a scale, and that's what gave you the molar mass. It's equal to the atomic mass in grams on the periodic table. And we know that 1 mole is also equal to the molar mass in grams. And then atoms, molecules, and formula units, those are quantities used in molar conversions to convert to the number of particles you have. So for instance, 1 mole can equal to 6.02 times 10 to the 23rd. Atoms, molecules, formula units, compounds, ions, etc. So this is another way to remember GMA, which now this is flipped. When it says number of particles, we're thinking of A for atoms, G for grams, M for moles, GMA, which is grams to moles to atoms, which these are the 4 steps that you need to know for a dimensional analysis is 1, know your unknown. So your known is your given, right? Your given, we always start with the given, and then the unknown goes in the last box. Then we're going to plan, which we were going to figure out where are we going from grams to moles or to atoms, and then we're going to do our dimensional analysis, which is our train tracks, and then we solve. So one thing I want you guys to do is when you're looking for GMA, which I've already previously told you, but let's remember again. Remember, these can be interchangeable. So you can go from atoms to moles to grams, or moles to grams, or moles to atoms. It doesn't matter, or grams to moles to atoms. It doesn't matter how you go. But just remember that whenever we're looking for grams, we're looking for the molar mass, which that you get from the periodic table. Whenever we're looking for moles, remember we're going to put a 1 in there. If we're looking for atoms, we're going to use Avogadro's number, which is 6.02 times 10 to the 23rd. Yes. Or, I mean, it doesn't necessarily have to say atoms. It can say molecules, formula units, compounds, ions. So let's look at this problem. It says how many molecules are in 55 grams of LiF? So starting off with the given, here it is, 55 grams. Oh, there you go. So that's what goes in our first part of our train track, and it's LiF. LiF2. And then our question's asking us how many molecules. So we want to go to molecules. Remember, molecules is kind of like if we're saying atoms, right? So from GMA, we are going to, starting with grams, we need to go to moles first, and then we can go to atoms. So grams, we're going to go to moles, and then atoms, which is the same thing as saying molecules. So we can go ahead and do our train tracks. Remember, we fill in our units diagonally down. So grams of LiF2 go here, moles goes here. 1, 1. For atoms, remember we use Avogadro's number, which is 6.02 times 10 to the 23rd. And for the mass, we had to add up 1L, which is 7. Sorry. And then F, which it's 19, but we need 2. So 19 times 2 gives me 38, right? So 38 plus 7 is 45. Please tell me I'm doing my math right. And then we go ahead and solve. Remember, when you are using your Desmos calculator, when you want to put the raised symbol, you need to put the one that has A raised to the B. That little one that if you want to do the exponent by. So you would type in 6.02 times 10, click A raised to the B, then put 23, and then times 55, and then divide by 45, which gives you 7.36 times 10 to the 8 molecules, which is right here at the bottom. So this one is just a lot more, like, basically in detail. This is how I did it in detail, so, and I wrote it nice. So K is your known or your given, which is 55. Your unknown, we're looking for molecules. Start with G, we're looking for molecules. G tells me I need my molar mass, which is what I put here. How do you get that? You add the Li, you add the F, which gives me, I put the whole thing though, which rounds to 45, so I put the 45 there. 6.02, remember the units cancel, so you're left with molecules. Let's go ahead and look at the next one. It says, in a 3.7 gram sample, there are blank atoms of gold. Oh, I didn't even mean to click it, so the answer is A. So starting off with your known, which is your given, it goes into the first one. Your unknown, we are looking for atoms. So atoms goes in the last one. So you're going from grams to moles, right? Grams to moles to atoms. And that's how we know how to set up our train track. You do the arrows, lines going down. Remember, we fill in our units diagonally down. So grams is here, diagonally down, grams. Moles, diagonally down is moles. Remember, mole is always 1. That's why you put a 1 there. For the molar mass, you have to look at the periodic table. Here's the molar mass of gold, 196.97. That's what I put there. And then for 8 atoms, I put Avogadro's number. Remember, don't forget when you are typing it into your calculator to hit that A raised to the B button for the number of atoms. All right, so how many grams of copper are in 4.6 moles? So starting off with your given is 4.6. You want to go to grams, so you can actually go backwards. We're just going from G, instead of GMA, we're starting off with moles, but we're going to go to grams. So moles to grams, you have 4.6 moles. Diagonally, moles is there, so they have a 1. And then right here should be grams. Grams of copper, you look at your periodic table, you get 63.546. 63.546, and then you multiply across. So 4.6 times 63.546, you get 292.31 grams of copper. All right, let's look at the next one. It says, how many grams are in 2.3 times 10 to the 24 formula units of KNO3? Go ahead and pause your video. That way you can work on the problem. All right, let's go ahead and see how we did it. I'm actually going to work it out on this side with you all. So our given is the 2.3 times 10 to the 24th formula units, which is kind of like saying atoms. So 2.3 times 10 24th, I'm going to put 4U for short. And we want to figure out how many grams. This is our unknown, grams. So we're going to go from formula units to moles, right? Because we always go to moles. Then we're going to go to grams. So formula units, then we're going to go to moles. Then we're going to go to grams of KNO3. Fill in our train tracks. Line going across. Oops, that looks super bad. Remember, to fill in our units, we fill in them diagonally down. So here, diagonally down, we should put formula units. Formula units. Diagonally down would be moles here. Remember, the easiest one to fill in is moles, because why? Mole is always 1. Now, for grams of KNO3, we have to look up the molar mass. So you look for potassium on your periodic table. There is only 1, so 1 potassium, 1 nitrogen, and oxygen. We're going to have to multiply this number by 3 because there's a total of 3 oxygens. Remember, sometimes you might need to distribute in if there's a parentheses. And then for here, for formula units, you put Avogadro's number, 6.02 times 10 to the 23rd. A hint, so if you ever see it where it has times 10 to the exponent, more than likely diagonally down, you're going to have Avogadro's number, just so you know. So we can do 3 times 16 plus 39 plus 14. I don't know what it is. It's 101.102 grams. And remember, you multiply across and then you divide. So then you get your answer. Oops, my answer is right here. 386.27 grams. So your answer is D for this one. Sorry, I'm going a little fast only because I'm already up with my hour. All right, next one. 1 mole of CBr4 has all of the following properties but 1. Identify the exception. So we're trying to look for the one that basically is false. So it says it contains 5 moles of atoms. Well, I see that we have 1 carbon and 4 bromines, which means there's 5 atoms in total. But then you would have 1 mole, so 1 times 5 is 5. So you technically have 5 atoms 1 mole of times. So that's true. So it has 5 moles, right? Because there's 1 carbon and there's a total of 4 bromines. But then you have 5 atoms, but then you multiply that by 6.02 times 10 to the 23rd. So you have 5 moles of atoms. Next, together, all the atoms weigh 332 grams. Well, if you have carbon, carbon has a mass of 12. Bromine has a mass of, it's around to 80. But there's a total of 4 bromines. There's only 1 carbon, and there's 4 bromines. So 12, and then 80 times 4 is 320. When we add that up, we get 332. So technically this is true because of the mass. It contains 4 bromine atoms. Does 1 mole of CBr4 contain only 4 bromine atoms? No, that is not true. Oh, so technically that's our answer. Because 1 mole has 602 sextillion atoms. How can it have 4 bromine atoms if it has that many? In 1 molecule of CBr4, it has 4 bromine atoms. But remember, this has 1 mole of those molecules. So it actually is 6.02 times 10 to the 23rd times 4. So that one's not it. It contains 6.02 times 10 to the 23rd carbon atoms. Yes, that is true, right? Because it says 1 mole of that many. And there's only one carbon atom, so that means there's 1 mole of that many carbon atoms, which is 602 sextillion. So the correct answer is, well, the incorrect answer, the exception is C. All right, topic number 2 is concentration of models. Go ahead and pause so you can do your drawing. Solutions are made up of 2 things. What dissolves, a solute, and what does the water does the dissolving, which is the solvent. Remember, if you were to have like a cup, and if you have your water, the water is your solvent. But let's say you wanted to dump in, I don't know, like sugar or salt. You want to dump in salt. This is a salt shaker, right? And you dump in salt. The salt is the solute. I don't know what happened. But do you guys like my salt shaker? So, concentration, it's the amount of substance per defined space, usually a liter. This is like saying your molarity. The more concentrated it is, the stronger it is. So kind of like if you were saying that if you have a Coke, right? And then you have one that had ice in it, but the ice melted. The one that is more concentrated is the Coke that never had the ice in it to begin with. The one that is diluted or is less concentrated is the one that has the ice or the melted ice. Remember, these are 3 ways or factors that affect solubility. It's how solute breaks down within the solvent, which is heat it, crush it, stir it, heat it, crush it, stir it. So stirring it, that's an easy way. When you mix it together, like think of sugar and like coffee. When you mix sugar and coffee, it's, well, I guess water. Hot water would make it dissolve faster. And then stirring would also make it dissolve faster. And then like say you were to have a sugar cube compared to fine sugar powder. The powder would dissolve a lot faster compared to the cube. So you'd have to crush the cube in order for it to break down. So let's look at this problem. It says, why does heating increase the speed at which a solid dissolves? Go ahead and pause your answer. All right, so let's look at answer choice A. It says, heating increases kinetic energy of particles, resulting in more effective collisions between solvent and solute. That sounds like it could be it. Heating causes particles to decompose, resulting in smaller solute particles that are more easily dissolved in the solvent. No, this more sounds like a one of crushing. Heating increases the ratio of solvent to solute particles. Do you add more things in there by heating things? I don't think so. Making it easier for solute particles to be distributed among the solvent? No, we're not adding things in there. Heating does not affect the speed at which a solid dissolves. No, it definitely does. Whenever you heat up an object, it's allowing it to heating does not affect this. Oh, yeah, it does. Whenever you're heating up an object, think of like when you're boiling water, right? At first, when you put the water on the stove, it's kind of still, but as time passes by and then your stove starts heating up, your pan heats up, then the water begins to bubble, and guess what? Those molecules inside are gaining their kinetic energy and they're moving around a lot faster. So A is the correct answer. All of the followings are ways to increase the rate of dissolving sugar, except, go ahead and pause. Remember the 3 things: heating, crushing, stirring. Heat it, crush it, stir it. Heat it, crush it, stir it. So, increasing the mass of sugar? No, why would we want to increase it, make more of it if we want to dissolve it? No, so A is the answer. Crushing the sugar into fine powder, that is definitely a way. You're making it smaller for there to be more contact with the solvent. Stirring with a spoon, yeah, definitely stirring helps push it and bring it into the water. Increasing the temperature of the water, yep, it definitely does help increase the kinetic energy of the molecules to dissolve. Molarity calculations. So, you are expected to, go ahead and read that, pause. Molarity. Molarity of the substance is in units of moles per liter, and molarity is also kind of like saying the concentration of something. I want you guys to remember the triangle, which, remember, it's kind of like the density triangle, except now with molarity. Except for here, this is the word moles, This is the liters, which is, I'm going to put an L and then a capital M for molarity. Yeah, molarity is capital M. So it says a sample of a 0.255 mole of potassium hydroxide was dissolved in water to yield 10 milliliters of a solution. What is the molarity of the solution? So first thing you need to do is identify your variables. I have my moles, right? This is moles because it tells you MOL is short for moles. And here I have my milliliters. When we are solving for molarity, remember it is moles divided by liters. So I need to convert this milliliters to liters. That's what I need it in. So how do we do that? Well, if you have 10 milliliters, you want to go to liters, milliliters on the bottom. You need to remember this conversion factor. For every 1 liter, there is 1,000 milliliters. So 1 liter, 1,000 milliliters. Another trick that you can remember is if you have 10, I don't see my little 10, and you want to divide by 1,000, you just move the decimal point over 3 times to the left. So if my decimal point is here on 10, you move it 3 times to the left. So 1, 2, 3. So my decimal point would be here. So I just have to add 1 more 0. So we have 0.01. So that is our liters, right? Because milliliters cancel. So for the moles, we said that we had 0.0255 moles. Divided by, we're going to divide by the liters, which we got 0.01 liters. Go ahead and put that into your calculator, and you should get 2.55 molarity. That is your answer. Let's go ahead and do the next problem. We're going to go ahead and calculate the volume of a 0.5 molarity of sodium chloride solution that contains 2 moles of NaCl. So, first thing we do is identify our variables. Go ahead and pause the video if you haven't done it yet. So 0.5 is our molarity, 2.0 is our moles. So we're going to calculate the volume, which is our liters. We don't know what our liters is. So I know my equation is molarity is equal to moles divided by liters. If we're looking for liters, you can just move around the equation by dividing by moles. Or, if you're not sure, remember, think of this triangle where we have moles, and then we have molarity, and then liters. We are looking for liters. So when we cover it, our equation is moles for liters is equal to moles divided by molarity. So our moles given to us on here is 2.0 moles divided by our molarity, which is capital M, 0.5 molarity equals 2. So you go ahead and divide 2.0 divided by 0.5, and that gives us 4. So remember that equation, or the density triangle, molarity triangle. So it says calculate the molarity in the solution which 360 grams of glucose, C6H12O6, are dissolved in enough water to make 250 milliliters of solution. So first things first, identify your variables. So here I have my, on this side, I have my volume, which is 250. That's my in liters. 360 grams. So I have grams, but remember, whenever we're doing for molarity, which we don't know what our molarity is, don't we need moles? But can't I convert from grams to moles? Yes, I can. So that's probably what I'm going to have to do. I'm going to convert that 360 grams of C6H12O6. I'm going to convert that to moles. How do I do that? I set up my train track. So grams goes down here. I know that 1 mole is equal to the molar mass of sugar. So you need to look at your periodic table. You need to look for carbon, hydrogen, and oxygen. We're going to get the molar mass of each one. Carbon has a mass of, what is carbon's mass? 12. Hydrogen has 1, oxygen has 16. Multiply by 6, multiply by 1, multiply by 6. 6 times 2 is 12, so 72, right? Is that correct? Oh, and this is supposed to be 12. I don't think my 2 showed. 1 times 12 is 12. 16 times 6 is 96. Add all of that up. 0, 1, I think 7, 8, 9. 180 is what I get. 180 grams. So now we're going to divide 360 divided by 180 grams of sugar, which is the molar mass, and I get 2 moles. Okay, so now I have my moles. And I know the equation for molarity is equal to moles divided by liters. Ooh, they gave me milliliters. So I need to convert from milliliters to liters. I showed you guys how to do that, right? Our given for the milliliters is 250. For every 1,000 milliliters, it is equal to 1 liter. So 250 divided by 1,000. You can just go ahead and do that, which I get, I'm going to put it here, 0, or you can move the decimal point over 3 times, 1, 2, 3, 0.25 liters. The 2 moles, for moles goes on top, so 2 divided by 0.25 is equal to 4. 8, that's what I meant. 2 divided by 0.25 is equal to 8, sorry. And this is another way to solve for it. I just kind of did it in a sequential step here. All right, topic number 4, making solutions. Go ahead and pause to read what you were expected to do. It says adding water to the universal solvent to a solution to make it less concentrated. That's what a dilution is, basically just adding more water. Remember, whenever you have like a beaker and you have a given amount of water, remember it's super dark, super concentrated, but when you add water to it, the volume also increases, but, well, not the volume, but the water is also a lot lighter. And that's because there's the same amount of solutes in there, but there's just more volume in there as well. So let's look at this one. It says, oh, and for the dilution, sorry, my bad, I almost forgot something important. You need this equation, M1V1 equals M2V2, which is the dilution equation where you're comparing the molarities to the volume. It says caustic soda is 20 molar sodium hydroxide and is diluted for household use. What is the household concentration if 10 milliliters of the concentrated solution is diluted to 500 milliliters? So first things first, go ahead and label our variables. So here I have 20 milliliters. This is my M1. And then we don't know what our M2 is, because this is originally what it is, and it's diluted for the household concentration. We don't know what it is, so we don't know what M2 is. If 10 milliliters of the concentrated is diluted to 500, so this is our V1, this is our V2, what is the household concentration? So remember, our main thing on this one is being able to identify your variables properly. So M1V1 equals M2V2. So M1 was 20 molarity. V1 is your 10 milliliters, right? So 10 milliliters there, equal to your M1. We don't know what that is, so I'm going to call it X. And V2 is 500 milliliters, sorry. If we want to solve for our X, our molarity, what do we have to do? We want to leave X by itself. So to leave X by itself, we're going to go ahead and divide. We're going to go ahead and divide by the 500. And what you do one side, you do the other. hopefully this works now. There you go. These cancels, and x is equal to, so 20 times 10 is 200. 200 divided by 500 is 0.4, which is 8. There we have it. All right, let's look at the next problem. It says, calculate the maximum volume of a 0.5 molar solution that can be made by diluting 400 milliliters of a 4.0 molar stock solution. So how do we do this? We're going to go ahead and calculate the maximum volume. We have our M1 and can be made by diluting 400 milliliters of 4.0 molarity stock solution. So notice how it says 400 milliliters of 4.0 stock solution. So we're going to call this one M2, and this is our V2 because 400 of that one. Technically, these are your M1, V1, but it's okay. It's still going to work out. So we're going to calculate the max volume. So we're going to calculate V1. So our equation is M1 V1 equals to M2 V2. We labeled this one as M1, so it's 0.50 molarity. V1, we don't know what it is, so we're going to call it X. M2 is the 4.0 molarity. V2 is 400 milliliters. That means our answer has to be in milliliters. So to do that, we're going to have to divide by 0.5 on both sides, right? These cancel out. So 4 times 400 is equal to 1,600. There you go. 1,600, and then we're going to divide that by 0.5. When we do that, we should get 3,200 milliliters. Okay, do you see 3,200 milliliters on your answer? No. Why? Because they're all in liters. So all I need to do is convert that 3,200 milliliters into liters. And I do that by using my conversion. I know that for every 1 liter, it's equal to 1,000 milliliters. So we get 3.2 liters. So your answer is B. And this is just another way I solve for it. And last topic is, well, not the last one, but solubility curves is the next one. Go ahead and pause so you can read what you were expected to do. So here, I'm going to move myself. Here we have where the word saturated, which remember, saturated means it reached the maximum amount of solute to dissolve in a solvent. And then on the solubility curve, the line will be on, the dot will be on the line. So the plot point is on the line. So it's on the line. For here, it says the solution has not reached the limit for unsaturated that will dissolve in the solvent. So more can still dissolve. Whenever it's unsaturated, remember, think of under, the dot will be under the line. So any point below is unsaturated, meaning you can still add more at that given temperature. And last but not least is super saturated. So the solution has surpassed the limit of solute that will dissolve. So more of it cannot be it can't be any more dissolved, or more has dissolved more than theoretically possible. So super saturated, I like to think of, you know, when you're making tea and you make it too sweet, there's too much of it. Unsaturated, there's not enough sugar in there, or like the flavor. And then super saturated is just right. So super, I want you to think over, you're overexcited, you're super excited, I don't know. The dot is above the line. So let's look at this problem. It says, according to the solubility curve, which of the following ionic compounds would be considered unsaturated when 80 grams of solute dissolved in 100 grams of water? So I want you guys to know something, and this is where a lot of you guys get confused, because it says on your y-axis is per 100 grams of H2O. ignore that where it says 100 grams of H2O. It's just letting you know that all these samples were dissolved in 100 grams of water, and that's how they made the chart. So it says 80 grams of solute, so 80 is here, 70 degrees Celsius. So 80 and 70, I'm going to plot my point. Here it is. So we're looking for NH4Cl. Here is the line for NH4Cl, right here. Now remember, we're focusing on the point, the location of the point. The point here is above the line, or the dotted line that I made. So that would be super saturated. We're looking for the one that is unsaturated at 80 grams. A is not it. Let's look for KCl. I'm going to turn this one into dashes. KCl, the dot is still above the line for KCl. So it is not that one. Let's look for SeSO4. So I'm going to put like a mixture of both. Still notice that the dot is above the line for SeSO4. So it is not that one. Let's look at the line for KNO3. I'll just do a solid line for this one. Sorry, it's not straight. So now, with the line of KNO3, the dot is below the line. So your answer is D. Because the dot is below, that means it is unsaturated with KNO3. And this one is just like a lot more drawn a lot more nicely. Okay, next one. It says, according to the solubility curve, which of the following ionic compounds would be considered unsaturated when 100 grams of water, a solute, is dissolved in 100 grams of water at 50 degrees Celsius? So kind of like the same thing in the other one. Go ahead and pause your video so you can answer the question. Temperature, 50 degrees Celsius, right? Temperature. Remember, we're ignoring the part where it says 100 grams of water, but the 100 grams of solute is important. So here's the 100 grams of solute. Go ahead and plot your point. If you meet in the middle, my point is there. All right, now, according to the solubility curve, we're looking for the one that's ionic. So look for the same ones. NH4Cl. And we're looking for the one that is unsaturated, remember. NH4Cl, right here. I don't know why my dots are not showing. There you go. NH4Cl. The dot is above the line for NH4Cl. That would make it unsaturated. KCl. The line is right here, kind of close. The dot is still above. Remember, we're always looking for the point of the dot. So the dot is above, so that is super saturated. So it's not that one. NaNO3. This is the line for NaNO3. Now the dot is below the line. So because the dot is below the line, this one is unsaturated. So it might be this one. And let's look for KNO3. This is the line for KNO3. I'm doing like a mixture of both. And for KNO3, the dot is above the line, so that would be super saturated. So the only one that is your answer is C. Okay, so let's look at another problem that I didn't get to go over for Unit 2. So here it says less energy. So first things first, this is the electromagnetic spectrum. This is how we see light in our eyes. The only light that we see is visible light, which is here, and this little part of the spectrum. That's the only part that we're able to see. But there's other waves and wavelengths and frequencies that we cannot see. So for instance, radio waves, sorry, radio waves, excuse me, have a long wavelength. Remember, to find the wavelength, it's from peak to peak, peak to peak, peak to peak. So the top part to another top part. They have long wavelengths. They also have less energy. Think of the wave. It's kind of like chilling. It's less energy. Doesn't have that much energy. Yeah. And then less frequency. Frequency is how many repetitions per second. Where over here on the right side, where you have like your gamma rays, has a bunch of repetitions per second. Let's say like half of this is 1 second. If you were to put this directly in half, this one only has 1, 2, 3 repetitions, maybe. And then this other half, they have so many, I'm not even gonna count that, but it has a lot of repetitions per second. So this one has a higher frequency. You can even see that it looks more excited, has more energy, and then the wavelength between the peak to peak is way, way, way shorter. So also that kind of coincides with the colors. The colors that are in the warmer sections, like the red, the orange, yellows, they're going to tend to have longer wavelengths, meaning the waves are going to be longer. They're going to have low frequencies and less energy. So it says, as a distant star moves away from the Earth, the light given off by the star has a measurable lower frequency. What happens to the wavelength and energy of photons of light when the frequency becomes lower? So, well, what happens to the wavelength and the energy? So if you have a low frequency, right, I want you guys to think of the wave. It's going to have a low frequency. That means not many repetitions per second. It would also have a long wavelength, right? From the peak to peak, it's going to be kind of long. And then it also looks like it has less energy and low frequencies. Where if you were to do another one that has it super high, like this one, right? It has a short wavelength, which is from peak to peak. It has a bunch of repetitions that has high frequency and high energy. So your answer for this one is A, because the wavelength is long and the energy is decreased. According to the picture below, which statement is false? The correct answer is D. So first off, let's go ahead and start from the very beginning. It says ultraviolet rays have high frequencies than microwaves. So we're looking for ultraviolet, which is this one here, compared to the wavelength of microwaves. Microwaves are here. Do ultraviolet waves have a higher frequency than microwaves? Yes, look, the circles are almost similar, but I have like 2.5 here. I only have 1 wave here. So that is true. That one's not it because we're looking for the one that is false. As the wavelength gets shorter. So wavelength is from peak to peak, and they get shorter the more right you are, right? Because the peak to peak is a lot shorter here. So as wavelength gets shorter, the energy increases, right? So yeah, that kind of is true because the energy also is increasing here. Remember here on this side, on the right side, where you have your gamma rays, X-rays, they have high energy, high frequency, but remember, wavelength is opposite. It would have a short wavelength, where here it's long on the left side. So next one, red light wavelength at 700 nanometers, which is right there, has less energy than blue light. Blue light is at 500 nanometers, and we know that the energy or the wavelengths also coincide with the wavelengths that we see here on our visible light. So here they're a lot longer, and then they actually get shorter and shorter, and they become more high energy. So does red light have less energy than blue light? Yes, that is also true. So this is not our answer. So the answer has to be D. Radio waves have the shortest wavelength. Radio waves, in fact, do not have the shortest wavelength. It's from peak to peak. They actually have the longest wavelength. So the answer is D. One problem that I'm going to go over really quickly is you need to remember the speed of light, Planck's constant, and the energy. These 3 equations, they will be given to you on your test. C is the speed of light, which is 3.0 times 10 to the 8 meters second. And H is 6.63 times 10 to the negative 34 joules times second. Those constants will be given to you. Let's do one problem. So it says the energy of a photon is measured to be 5.8 times 10 to the negative 22 joules. What is the frequency of the photon? Sorry. So first things first, you guys have to identify your variables. So 5.8 joules, this is the energy. So here we have E, energy, right? This is your energy. What is the frequency? So we don't know what frequency is. To choose our equation that we're going to use, we have to make sure that we have both E and F. So the one that has both E and F is this one here. So we have E, F, and remember H is Planck's constant. That number is already given to you. So you kind of just have to plug them in. Sorry. Sorry guys. So here's the equation. E is equal to H. V is for frequency, but you can put an F, it's fine. I'll actually change it to an F. That way there's no confusion. So you go ahead and plug them in, and then you just solve for F, which is your frequency. And you get your answer as 8.75 times 10 to the 11th hertz. Okay, so you guys have made it here to the last slide, which is super, super awesome. Go ahead and put your signature on there, which this lets me know, this is not even my signature. This lets me know that you have finished watching the video, and this will get you 100 on your review. I want to thank you for staying on here, but wait, do not hang up the call. The reason why it's so important that you guys watch the review is because I heard from a little birdie that they used some of the previous exam test questions for your semester exam, which I used the previous test questions for the review. So if you watch this review and went over it, practice the problem, you guys should do fine. You're probably going to see a lot of similar questions on there, which I'm sorry, but other teachers are doing it too, so don't even worry about it. But yes, remember that I can change your semester exam grade from your raw score. Like whatever you get on your semester exam, your raw score, change to your like exit ticket grades. I'll change it to whatever you got there if they're low, if they were lower. So yeah, thank you guys so much for watching. I know this video was long, and I'm so sorry. So that we literally didn't have that much time to review. But if you guys have any questions, just let me know. You can let me know up until like the morning of the exam. After that, I can't help you. But you will be given all your reference material, your periodic table, your periodic table, Vesper chart, the reference materials, all that will be at the end of your exam. So when you're needing it, scroll to the very end. Remember, your calculator will also be issued on the Elluminate exam. But good luck, guys. I hope you all do really well. So maybe when you want to review any of the problems, please go back and study them. But if you have any questions, let me know. Thank you so much. Bye, guys. Good luck.